Hey guys, welcome back to quantum mechanics. Let's see. Last time we left off, we had started to talk about uh, what's called the quadratic Stark effect. So we had just trying to remind myself here. So we had uh, been talking about a couple of examples in non-degenerate time-independent perturbation theory, and we were slowly working our way up the ladder as far as complexity goes. And we had started to talk about this quadratic Stark effect. Okay, so this is basically an electron and a hydrogen like atom in an electric field, external electric field. And we'll get to the details in just a minute. But the first thing we said was that a lot of these real world instances, the solutions are messy and hard to come by. But there are some things that we can use, that are at our disposal that make our life a lot better. And one of these things is called selection rules. This is especially important when you're talking about transitions in an atom or even in scattering. There are different transition rules or selection rules that tell you right off the bat if certain matrix elements are going to vanish. So basically, they arise because there's some symmetry of the Hamiltonian, and for the example we'll use today is parity. So this is the discrete symmetry of the discrete transformation of spatial inversion. And these selection rules were based on the idea that if the observable that we're using to span the space, if that operator commutes with our perturbation Hamiltonian, then it tells us that the matrix elements that we're going to be interested in computing, remember when we can compute for in perturbation theory, we're always interested in these matrix elements, right? And what it tells us is if this thing is true, if this thing commutes with if A commutes with the perturbation Hamiltonian, that all of these matrix elements are going to be zero unless the two states are the same, right? We went on and proved it. And in particular, we considered, so I showed you one example, which is the perturbation Hamiltonian is some function of space. So in this case, we let it be z, right? And lambda is just some constant, so it's going to be our parameter that we're going to expand in if we apply perturbation theory to this case. And one thing we notice is that this operator is invariant under rotations about the z-axis. Right, so this implies that our angular momentum operator that is responsible for these rotations commutes with the perturbation Hamiltonian. Right, so we know that LZ basically commutes with Z. Right, so that's telling us that these guys have they're compatible, and so they share the same eigenstates. Okay, so we can state the above condition that this guy is going to be zero. If we were to try to compute this thing, it's going to be zero unless m1 equals m2, right? In the case where h1 is parity invariant, so let's say we considered z squared instead of z, then that's telling us that the matrix element between states of opposite parity is zero, right? Because this guy is even parity, and if one of these is even and one of these is odd, it's going to be zero. Okay. So how do we interpret equation 33, which is this guy, right? This thing about these matrix elements. Let me get back where I was. Okay. And right, and I was trying to give you this idea that to say that these guys commute is telling you that H1 doesn't carry any A, and I'm putting this in quotation marks. So in other words, it's not this Hamiltonian doesn't impart any A, whatever A is. So if H1 is some proportional some like in the case of above, here's H1, the case above H1 was Z, proportional to Z, and there we saw that it commuted with the angular momentum operator LZ, and so we would say that H1 doesn't carry any LZ. Okay, it's just a way of saying things, even though it might be confusing as hell, and I'm probably making it more confusing. So anyway, so yeah, so we've been talking about that, right? And so what we came up with was that the selection rule that we had written down just reflects the orthogonality of the eigenstates with different values of A prime, right? So if H doesn't carry A prime, then this thing, or H doesn't carry any A, then this thing in parentheses is the same as just a ket by itself, right? So H doesn't impart any A, and in that case, you can see that that it's the selection rules is telling us that these eigenstates are orthogonal. Okay, and so I'd left off with a special case of this, which is called the Wigner-Eckhart theorem. This is when you're dealing with angular momentum states, and you can write your operator as tensor operators. So typically they'll be like position operators, and those we can always write in terms of tensor operators. And I don't believe we did a lot of this when we talked about angular momentum. I don't know if we did any at all, really. But if you need kind of a refresher as far as writing these operators in terms of these tensor operators, have a look at Sakurai. I know he covers it, and I believe Shankar does this too. I believe Shankar probably does a better job of discussing it than Sakurai. Okay, so we had left off with this statement of the Wigner-Eckhart theorem, which tells us that these matrix elements are zero unless J1 or unless J2 is between J1 minus K and J1 plus K, right? So that's the addition of angular momentum, basically, right? So this thing's imparting some angular momentum J onto this state, and so then these two, the resulting eigens, or the resulting ket, bra with this resulting ket would be zero unless these conditions are met. Right. So this guy is carrying K angular momentum, and Q would correspond to the LZ quantum number. Okay. Right. Yeah, I think I just said that. So a typical example would be go back to our Hamiltonian, which is linear in Z. Right. The Z operator we can always write in terms of these tensor operators as a T10. Right. So it carries L squared quantum number, but its M quantum number is 0. Right. So that means that I can write down this matrix element, and right off the bat, I don't have to do any tough or complicated calculations. I can just use the Wigner-Eckhart theorem, which tells me that J2 has to be J1 plus or minus 1, right? Or run from J plus 1 down to J1 minus 1, right? From the addition of angular momentum. And that M2 has to be equal to M1, right? Because it's not imparting any angular momentum in the Z direction, right? Or we could do slightly more complicated cases where the Hamiltonian goes like either X or Y. And in that case, this thing's going to be some linear combination of these T1 plus or minus 1s. Okay, so these are a lot like the spherical harmonics, right? Spherical harmonics are wave functions, and these are operators, but the notation is basically the same. Okay, so these matrix elements are going to be the same thing we had before, because it's still imparting this 1 down here, but now the M1 and M2 have to be different, right? So M1 or M2 has to be, or M2 has to be M1 plus or minus 1, right? Depending on what this value is up here. Right. So another example of these types of operators are ones where the operator's not parity invariant, right? So it's not what we would call parity even, but it's a case where it's parity odd, right? So in other words, so this is the Wigner-Eckhart theorem, and let's kind of independently we can talk about selection rules coming from parity. Okay, so not just the addition of angular momentum, but here we're talking about parity. Okay, so remember what parity does. So if I take an operator like x and I hit it from both sides by the parity operator, right? If it's odd, it's going to flip sign. If it's even, it keeps the same sign, right? So what it tells us, what we know, or what it tells us is that when x acts on a state with definite parity, it's changing the parity of the state. In other words, because this guy x doesn't commute with our, the parity operator, it's going to change the parity of the state, right? Um, right. So, and since we only have parity even or parity odd, it's telling us that the matrix element of x between eigenstates of parity is going to vanish unless those two states have opposite parity. Okay, hopefully that makes sense. And so we can generalize this not only to x, but just any operator that's odd, right? So if this is the case, if the operator is odd under parity, then these matrix elements, and I just noticed that these alphas should be A's, these matrix elements are going to vanish because this guy is going to impart parity onto this guy, and so this thing will be zero unless these two have opposite parity. Okay, so now we've got two ways of two nice little selection rules. One coming from the Wigner-Eckhart theorem, or the addition of angular momentum, and the other coming from this idea of parity. Okay, so what we can do is we can combine these two, right? And when we combine these two, it gives us a tool that we can use to quickly rule out certain transitions, or to quickly compute certain transitions. Okay, so we'll consider an example where, let's say, instead of working with generalized angular momentum, we're working with orbital angular momentum. So our quantum numbers are now L and M. Okay, so we can rule out possibility of L2 equals L1. And that's because that states of orbital angular momentum have definite parity, right? So L1 would have an angular momentum like this, and L2, because it differs by one, it's 2 is equal to 1 plus 1. So it's going to flip the sign, right? So they have opposite parity. Okay, and this is what's called the dipole selection rule. And we'll come back to it. Okay. So that was all general stuff about selection rules. And now let's see how we can apply them. Okay, so we're going to get down to this quadratic Stark effect. Okay, so we want to consider this example. It's a hydrogen atom, and we're going to be focused on the ground state. So in terms of N, L, and M quantum numbers, it's going to be a 1, 0, 0 state. Okay, and we're going to put this hydrogen atom in an external electric field. Right? And we're going to point this electric field in the z direction. Okay, so my electric field looks like this. Okay, and what we'll see is, so this is called, it's kind of a generalized Stark effect, and we'll see why it's called the quadratic Stark effect in just a little bit. So the first thing we have to do is construct the perturbation Hamiltonian. Okay, and instead of just pulling it out of the hat, I thought I'd take, just a couple minutes to remind you how we construct Hamiltonians in quantum mechanics, right? So the first thing we want to do is determine the classical counterpart. So that means we're going to have to talk about classical electromagnetism. Okay, unfortunately, so it's just for a couple minutes. So don't worry about it. All right. So we're going to write down the classical counterpart and then quantize any observables. Okay. All right, so let's set up our coordinate system where R1 and R2 are the position vectors of the electron and the proton, respectively. Okay, and phi is going to be the static potential, the electrostatic potential due to our electric field. Okay, because we know that this thing's going to interact via this this electrostatic potential. Okay, so the classical Hamiltonian that we would write down would be the charge, right? So in this case, this would be the electron, times the electrostatic potential plus the case for the proton. Right? So this is what our Hamiltonian looks like. Or we can use the fact that our electric field is given by the gradient of the potential, and then rewrite this thing as a dot product between this vector difference and the electric field. Okay, so that means our Hamiltonian is going to look something like this, right? Where r here with no subscript is basically the relative coordinates. Okay, and we always take this limit that the electron is much less massive than the proton, right? So in this limit, this thing goes to zero, this ratio goes to zero. In the center mass frame, the proton's basically sitting at the origin. Okay, all right. And this is what we call the dipole, the electric dipole interaction, right? It's just the analogy of the magnetic dipole interaction, right? And in fact, we can define the dipole moment, the electric dipole moment of the electron, as minus E times the position vector r, right? And so that gives us an equation that looks very similar to the magnetic, what I call it, the magnetic dipole interaction, right? Just remember that these two mu's are different, okay? Okay, so for our particular case, we're putting the electric field in the z direction, okay? So that means that this guy is going to just reduce down to this, okay? And now what we want to do is now we want to quantize this thing, right? The only real observable here is the z coordinate, all right? So all we have to do is just promote z to be an operator, okay? All right, so let's get back now to computing the corrections from perturbation theory, okay? So what we want to do is we want to compute basically the corrections to the ground state energy of putting this thing in an electric field, all right? And so we start at first order, right? And so remember, the first order correction is just the perturbation Hamiltonian sandwich between the unperturbed states, right? And so little e and big E are just constants, right? So we can pull those out. And I have the matrix element here of Z between the 1, 0, 0 states, right? However, now using our selection rules, we can already rule this out. We can already set this to 0 because we know that these guys are parity even, right? Remember, this middle number is the L, right? And so the parity of this state is going to be minus 1 to the L, or minus 1 to the 0. Right, so this is even parity, this is even parity, and we established a few minutes ago that Z is odd parity, right? And so that means that by our parity selection rules, this thing's going to be 0, okay? Note that you could have just as easily applied the Wigner-Eckhart theorem that tells you that this thing's going to be 0 because Z, remember, carries angular momentum, and so it's going to impart some angular momentum on this L1, right? And that's not going to work out, okay, because they're both 0 states here. All right, so we have at second order, so we have to go to second order if we want, the first, if we want to compute a correction to the unperturbed energy eigenvalue. All right, so I plug this back into the general expression that we had before, right? So it's going to be everything gets squared in the numerator, remember, and we're going to sum over these states in LM, right? And remember, so this prime here on this NLM is telling me that N, L, and M can't be the same in L and M over here, right? So it can't be the ground state, okay? All right. And we know that we're dealing with a hydrogen atom, so we can write down what this thing actually is. Right? And so you can write down E11 minus E NLM, right? And this is the minus 13.6, right? And it scales like 1 over n squared. Okay, so what you see is that as n gets bigger, what's going to happen? So this thing's going to go to 0, and this thing's going to become more negative. Right? Okay. the minus sign is always kind of trips people up when you're talking about these bounded states. So just if you get confused, just stop the video and try to convince yourself. Maybe even draw a picture of what the energy scale is going to look like. Okay, so this is what we want to compute, but unfortunately, it involves an infinite number of terms. All right, so that would take a long time to do. And so what we're going to try to do is use our selection rules to try to at least eliminate some of these, right? So instead of infinity, we've got maybe infinity divided by 2. Okay, that's a joke. But so let's try to see what we can do here. Okay, so the first thing we can do is we can reduce the number of matrix elements we need to compute by using the dipole selection rules, right? And because we have L equals 0 over here, that tells us that how am I trying to get the dipole selection rule? Let's go back. I just got lost here. Right. So the dipoles. So we have to have because this guy. Where are we? This is all right. So we have Z that's going to impart angular momentum here, right? And so L has to be this angular momentum plus or minus 1, right? And so it's going to range from 0 to 1, but we know it can't be 0 because that state would be even parity, right? And we have an odd parity operator, or Z operator. And so that tells us that we can rule out any states that have L equals 0. Okay, so we now know that L has to equal 1 and M has to equal 0. Okay, and likewise, you could get the same thing by imposing the Wigner-Eckhart theorem. Okay, so we've narrowed it down now down to these matrix elements. Okay, so now this case, we instead of summing over generalized L and M, we at least know what L and M are, right? And you can actually do this. You can actually compute this sum, and I'll encourage anybody that's interested to go look at the Merzbacher book. It's extremely messy, as you might have guessed. Okay, so what I want to do in the interest of time and the fact that I don't want to do this hard calculation, let's see if we can get a ballpark estimate. Okay, so the first thing we want to notice is that the magnitude of the denominator, this guy back here, is going to grow as n becomes large, right? Oops. Right, as n becomes large, remember this thing's going to get closer to 1, so it's getting larger, right? And because of the minus sign, if we pull out the denominator, right, it's going to give us an upper bound. Okay, the denominator from the first term. Sorry, I blanked out there for a second. So we're pulling out the denominator of the first term, and it's going to give us an upper bound. Okay, so this is where you need to really convince yourself of what I'm saying. So this might be a good time to stop the video and think about what I'm saying here, what I'm doing here. Okay. Okay, so we need to, in that case, if we want just the upper bound, we can compute this thing, right? This matrix element. Okay, and squared. All right, and remember we're taking the sum. Okay, so how do we do that? Well, let's see here. So we have, we know that this guy, okay, hold on a sec. Let me think about this. I had this worked out in my head before I started. Okay. Hold on just a second. Okay. Yeah, I believe that, let's see. Yeah. Yeah, this N10 here is the same as NLM. Remember, NLM, we know from our parity selection rule that it should be, L should be 1 and M should be 0. Okay, so I think I kind of bounce back and forth between the different notations, but just keep in mind that we know what L and M are. Okay, so we want to compute this thing, right? So it's this guy right here, right? And so I can rewrite this thing by just expanding it out. And so that's what I've done, right? So here's the NLM or N10 and the NLM N10 here. Right? I've just unfolded this kind of conjugate squared thing. And now what I'm going to do is use a trick. So if I can add and subtract something, right? And what I want to do is add and subtract this term, right? These matrix elements. Now remember, these things are zero, okay? So we're not really even adding and subtracting anything. We're just putting in a couple of zeros, okay? But what I can do now, right? Remember, this prime is telling me that I can't sum over all values of NLM because some are forbidden, right? But what I can do is pull one of these terms in, or pull this term in, right, into here, and this thing becomes a sum over all of NLM, okay? And if that's the case, then this thing, the sum with these two guys right here, is the equivalent of multiplication by 1, right, in between uh, this state and this state, okay? So what that does is it gives me something that looks like this. So it's the matrix element of z squared, right? And then subtracting off this piece, but this piece we've already said is just 0, okay? And so finally what we have is this matrix element, right? And you can rewrite this z squared as r squared over 3, right? Remember, r squared is x squared plus y squared plus z squared, right? And then you can go and look in any quantum book you want. And you can see that where this matrix element is evaluated. And when you calculate it, you get 3 times the Bohr radius squared. Okay, so this is probably a matrix element that you've computed before in your lifetime. Hopefully you can remember, but just go check it. Okay, and I think at this point, if you're following along in Sakurai, there's a typo here. Uh, but so just be careful of that. Okay, so what it's telling us is that we can take this matrix element and we basically get this Bohr radius squared, right? And so the second order energy correction, right, has an upper bound. That's what we were computing, and it looks like this, okay? Or if I put in the numbers, it's telling me that the upper bound of our second order energy shift goes like the electric field squared, okay? And this is where the quadratic part of the quadratic Stark effect, this is where it comes from, okay? And it turns out you can also get a lower bound on this energy correction by keeping just the first term in the sum, right? Because each term is going to be higher, right? Each term is going to be higher in energy. Remember, this minus sign for the bound states takes some work to get used to. So it's telling us that the upper bound or the lower bound is going to be this. So all we're doing is keeping the first term in the sum. Okay, so the n equals 2 term, right? And this guy now I can compute, right? Because I have we know it's non-zero, right? Because I can see by the Wigner-Eckhart theorem that there's going to be a non-zero piece of this. And you can compute it, and I'm pretty sure that you have already in the homework, because when I look at this answer and I see this factor of 2 to the 15th, it reminds me of a homework problem that I'm pretty sure I assigned. But this is another matrix element that you can look up, and you find that it looks something like this, right? Which, if I put in the numbers, is about a half of the Bohr radius squared. So in the end, we get a lower bound for our second order energy correction looks like this. So what we find is that, you could have computed this sum, this guy. So this is what we wanted to compute, the second order energy shift. You can compute it exactly, right? But instead we used some simple arguments and just got a ballpark figure. So we know that it's got to be somewhere between this number and this number. Okay, so you notice that these only differ by basically a factor of 2. Okay, so we can get the order of magnitude correct by just using these simple arguments. All right. Okay, and like I said, Shankar discusses this quadratic Stark effect, and the page number might differ depending on the edition that you have of Shankar, but he does do it, and it's a different way of estimating the second order energy shift. Okay, so that's it for today. I'll see you on Wednesday, and just send me email or let me know somehow, smoke signal, any way you can if you have questions about anything. Okay, and I'll talk to you soon. All right, have a good one.